Hello, welcome to electronic system design. In the last lectures, we were discussing about the static CMOS logic, where we saw that in static CMOS logic, we have pull-up network and a pull-down network. These two networks are dual of each other, and one of them is on, then other one will be off, and vice versa. So, because of this property, this dual property, there is no static power dissipation because there is no current path exists from ground to supply in steady state. In transient it is there, but in steady state there is no static power dissipation. And then we saw a basic NAND gate, and we derived the output characteristics, or the truth table we call it, which is a 2-input NAND gate truth table, and we saw how the output is generated using that circuit, CMOS circuit. We have 2 PMOS on top in parallel and 2 NMOS in series for the pull down network, and we generated the output characteristic for multiple vectors of input A and B. So, there are 4 combinations of A and B, and we saw the output is generated from this circuit. So, that was the static characteristics we saw, and we saw there is no static power dissipation, and we saw that the delay of this circuit is actually dependent on two things. One is the pull up or pull down resistance and the output node, which is the capacitance. It acts as a capacitance, and this capacitance comes from nothing but the next stage which we are going to connect to this circuit. So, let us assume that the number of gates we connect to our actual NAND gate is fixed. It means the capacitance, the load capacitance value is fixed to some value, let us say 100 femtofarad or 200 femtofarad and so on. So, that value, let us for time being we consider that the capacitance is fixed. Now, in today's lecture we are going to discuss the switching delay of these gates. In last lecture we discussed only the steady state value, which is high or low only, no timing information. Today we are going to discuss the switching delay model, and we come up how the input pattern or how the sizing of these transistors impacts the delay. Delay is very important parameter because delay dictates how fast we can put the transition or how fast our circuit will be operating. So, all the time we want to go for faster and faster electronic devices, let us say 1 gigahertz, 2 gigahertz, 3 gigahertz. So, the delay of these individual gates actually dictates how fast we can go at the system level. So, it is very important to understand how we can optimize our individual gates, NAND gate, NOR gate, all these gates, so that we achieve a very less or very optimum delay at the system level. So, today let us discuss the switching delay model for these gates. So, to make this model, we assume that a MOSFET, a transistor where we have this input as A at the gate, this is equivalent to a resistance, which is the on resistance of this MOSFET, and an ideal switch. So, this switch is an ideal switch which gives always on, it can turn on and off with no resistance of this switch itself. So, this switch is dependent on the input A. So, now we have a ideal switch in this delay model and the resistance which is the source to drain resistance, or we can say the R equivalent of this MOSFET. So this is the equivalent model of a MOSFET we are assuming. Now let's draw these gates individually. So let's first consider a PMOS or a NAND gate, two input NAND gate, how it look like. So on top we have two PMOSes in parallel. It means we have two instances of such a model. This is RP. RP is the resistance of PMOS, and this switch, ideal switch, is dependent on signal A. Similarly, the other MOSFET, this is PMOS, assuming the width and length is same, then the resistance is also RP, and this MOSFET is dependent on the signal B. This is the pull-up network. For the pull-down network, we have two NMOS in series. It means we have two instances of this model where the equivalent resistance is, let's say, Rn, the resistance of NMOS, and the switch is dependent on B, and the other model, other instance of this model, again the resistance is Rn, but the ideal switch is dependent on model A, on the input A. The output, this output node is nothing but a capacitor, which is the load capacitor from the next stage, and we call it, let's say, CL. So this is a two input NAND gate. So this is the equivalent model or switch delay model of two input NAND gate. Similarly, if we want to see the inverter which we discussed last lecture, we can make the equivalent switch delay model. For an inverter, we have one PMOS on the top. It means one instance of this model. Resistance is RP. That A bar and B bar. So the input is A bar. This is the output node, which has a load capacitance CL, and in the pull down we have a NMOS transistor where this resistance is Rn, and the switch dependent on input A. This is the model of inverter. Let's see one more gate, which is also very common gate, which is NOR gate. So two input NOR gate. In two input NOR gate, we have two PMOSes in the series on top as a pull-up network. So we have first PMOS, this is our P, control signal is, let's say, B bar, and the other PMOS in series, Again, assuming width and length are same, so this is Rp and the control signal is A bar, and then we have this output node with a load capacitance CL. For the pull down network, we have two NMOS in parallel. So let's say we have, this is the first NMOS, resistance is Rn, control signal is A, and this is another instance of NMOS, resistance is Rn, and the control signal is B. So this is a 2-input NOR gate. So here we see we have switch delay model of 3 various gates: NAND gate, inverter and NOR gate, and by assuming a transistor as a resistance in series with a ideal switch, we can replace all the PMOS and NMOS by this equivalent model or delay model, and we can make a complete delay model of the gate. If we see this carefully, this NAND gate, we have 2 PMOSs on top and 2 NMOSs in series at the bottom. Now the delay is, as per the definition, when the output rises to the 50% compared to when the input is applied. Let's say input is applied at time 0, the output start rising. When it reaches 50% of VDD, that time from the time 0 is called, let's say, the rise delay. This delay depends on how much the capacitance CL is and the RP, the overall pull up resistance or pull down resistance. Let's say we are going high, it means the pull up network is active. Pull up network is pulling this output node to higher value. So CL and the effective resistance of pull up network. If we are talking about NAND gate, we have 2 PMOS in parallel. It means depending upon the input, whether A and B both are 0 or one of them are 0, we may have a case where both of the PMOS are on or only one PMOS is on. So if both of the PMOS are on, both of them will be drawing the current from VDD to load, and this load capacitance CL will be quickly pulled up to VDD in first case. In second case, if A is 0, B is 1, it means the one PMOS is on and one PMOS is off. So this output CL, the capacitance, is pulled up only by one PMOS as compared to the previous case where we have 2 PMOSs to pull up. Now this pull up will be a little slower because only one PMOS is bringing this output node up. It has certain the current limits. The current is less compared to the previous case. So the rise at the CL will be slow. It means it take more time in rising to 50% or to 100% of VDD. It means the delay value now depends on CL as well as the input pattern also, because if we have both of the input 0, we have a faster turn on, but if the input is one of them is 0, one of them is 1, then the output rises slowly. It means the delay of this gate is dependent on the input pattern. So not only on the circuit's elements for PMOS and NMOS or the actual load capacitance, the delay of the gate this NAND gate is dependent on the input patterns as well. This is the case with all other gates as well. For example, NOR gate also the case is same. So, we have a delay which is dependent on the pattern of inputs. So, let us study that in a little detail. Input pattern effects on delay. So, as we discussed, let us draw the switch delay model of NAND gate again. This is Rn, this is Rn, this signal is B, this signal is A, and at the load, at the output node, we have the load capacitance which is CL. However, if we see carefully, this NMOS for signal B and this NMOS for signal A, they are joined at this point, and whenever we have a junction of current, junction in these components, we have a associated capacitance as well at that point. So, let us have this capacitance which is the C int or the intermediate node capacitance. We call it C int. This is also significant because at this point there is a wire which is connecting these two NMOSes together, and this wire can have its own capacitance which we are calling, let us say, C int. So, now we see that the delay is dependent on the pattern of inputs. So, let us first consider a low to high transition. So, for going from low to high transition at the output node, we can have two cases. One is when both input goes low, it means both transistor, let's say we call it P1 and P2. This is, let's say, N1 and N2. So we, in the first case, when both inputs are going to low, it means P1 and P2, both transistors are turned on. If both are turned on, then this output node will get current from VDD through both of these PMOSes. So half the current will come from P1, half of the current will come from P2. It means the overall resistance which are in parallel, Rp and Rp, this becomes effectively half, which is Rp upon 2. So for this case, when both inputs go low, the delay is 0.69 times upon 2 into CL, the load capacity. In the other case, when one input goes low, it means either P1 is on or the P2 is on. So the output node is getting current only from one, the other one is off. So the effective resistance is Rp only. So the delay is 0.69 times Rp into CL. So we can see here this delay in the second case is actually double of the delay in the first case. So the delay for both inputs going low is very less compared to this case where only one input goes low. Now let's see the transition from high to low. So this high to low transition can happen only when both of A and B, both of these signals are going to high. It means N1 and N2, when both are on, then only the output will be pulled to ground through these N1 and N2. So there is only one case, both inputs go high. And we can say the delay is 0.69 times twice Rn into Cl. If we see carefully, we have the effective resistances 2Rn because this Rn for N1 and Rn for N2, they are both in series. So the effective resistance is Rn plus Rn, which is 2Rn. So the delay while going high to low is the worst case delay in all this analysis. If we see, let's assume Rn and Rp both are same, then we have the delay here is x, then we have here the delay is 2x and here the delay is almost 4 times. So here we can see, depending upon the input pattern, the delay of this gate can vary from x to 4x all the way. X is, let's say, 100 picosecond, then the worst case delay of this gate is 400 picosecond. However, for one pattern the delay is 100 picosecond, and for the another pattern, while going from high to low transition at output, the delay can be as high as 400 picoseconds. So this we need to take care while designing our digital gates. Now let's see, even in these A and B, if we see, right now we have assumed, while going from high to low or low to high transition, when we are assuming both inputs go low, we are assuming both of the inputs are switching simultaneously. However, this is not the case, this is not a general case. Generally, the signal can switch any time compared to the other one. So in real case, a single signal can switch on and off at the same time the other signal is static. So at that time, we have one more analysis to do, where the inputs are not bind, they are individually changing. So let's see that. So we are still discussing delay dependence on input pattern. So we have an again NAND gate, 2 input NAND gate, which looks something like this. This is transistor, let's say P1, PMOS 1, and this is PMOS 2. This is N1 transistor and N2 transistor, 2 input NAND gate. And if we do various analysis for multiple input patterns, then we have this kind of graph. So this is a general simulation done for PMOS and NMOS of these particular width and length. This is 250 nanometer technology, and the PMOS width is 0.75, NMOS width is 0.5 micrometer, length is same, 0.25 micrometer for both of PMOS and NMOS. Now we have these input pattern data. In first case, we have A and B, both are going from 0 to 1. So this red graph shows the input, whichever input is changing, and these blue, green and purple, they are different cases. If we see here, when A is 1 and B is transitioning from 1 to 0, it means the PMOS is off and PMOS P2 is turning on. So P1 is off and P2 is turning on. So only P2 is pulling up this node output, this load capacitance CL, from 0 to VDD. This is VDD value. So this is, you can say, very sluggish response. This is the midpoint, let's say. So the delay is from this point to this point. So this is the delay in case A is 1 and B is transitioning from 1 to 0. This is the one. If we consider the other case where we have A is transitioning from 1 to 0 and B is 1. Here we have one more thing to note here is this intermediate point, this C in, because when B is high, B is 1, it means this node is already charged to V output if the B is always 1 from the previous state. So this C int is also VDD if B is 1. If B is 1, the C int is already charged to VDD and now A is turning on. A is going from 1 to 0. So this node C int need not to be charged to the high value because it's already charged to something. So B is 1, we have this C int already charged to some value. If A and B both are going from 1 to 0, means both P1 and P2 are turning on and both N1 and N2 are turning off, it means C int is don't care because this intermediate node, we are not worried about this voltage. This output only need to be pulled up by P1 and P2. So we can see this is a fast rising compared to all these other two cases and the delay is less. So this is the delay in case of both of the inputs A and B are going from 1 to 0. So there are various different cases we have to simulate for different data patterns. In the first pattern we have A and B both are changing from 0 to 1, then we have 67 picosecond delay. When A is stable as 1 and B is transitioning from 0 to 1, then we have 64 picosecond. Here A is changing from 0 to 1, B is stable at 1, then we have 61. When A and B both are going from 1 to 0, both are transitioning at the same time, then we have only 45 picosecond delay, which is the best case delay we can say. Other case we have A is stable as 1, B is transitioning from 1 to 0, then we have 80 picosecond, and the other case where A is transitioning from 1 to 0 and B is stable at 1, then we have 81 picosecond. This is the maximum delay and this we can call it the worst case delay. The maximum delay and the minimum delay, these are very important numbers. This we call it the best case delay and the worst case delay. These two numbers are very important in characterizing our circuit, or when we make a complete system, that time we need to know at what time I can expect the output to be stable of this gate, because after this delay only we can assume the output is stable, otherwise the output is still in transition. So the best case delay and the worst case delay, these are the important numbers for a gate which we need to know while designing these logic circuits. So now we see how we can make a complex CMOS gate compared to these NAND and NOR gate. These are still fairly simple. We can even increase the complexity of these gates and see how they look like, or how do we do sizing or the design of these logic gates. So transistor sizing of complex CMOS gates. So let's draw a little complex logic gate. This is VDD supply. Let's say we have a logic gate something like this, where we have PMOS connected like this. This is the output node. So this is our PUN or pull-up network. In the pull-down network, this is the dual of this circuit. This is pull-down network. So this is actually 4 input, a complex CMOS gate. Let's name the inputs. This is, let's say, input A, B, C and D, and the same input goes to the pull down network in this A, B, this is input C and this is input D. If we calculate the function of this, the output actually we can write is D plus A into B plus C whole bar. This is the implemented function of this complex CMOS gate. Now we want to understand how do we do transistor sizing, because the width and length of these transistors are at our hand, which we can optimize to get a similar delay. Though length is generally fixed by the technology, if let's say we are using 250 nanometer technology, length is generally fixed to 250 nanometer, but the width we can change to increase or decrease the resistance of individual PMOS and NMOS. So now if we see this carefully, this PMOS is in series with, is in parallel with this B and C. This B and C are in series with each other. So ideally we want to have this path through A should have same delay or the same resistance as the path from B and C. So B and C should have the same resistance as compared to the signal through A, the current through transistor A. And this we can write, for example, we are using a delay of 4 unit. here, then this B are like 8 and 8, and the D is, for example, 4. So, this is how we can do transistor sizing. Similarly, for the pull down network, if let us say we assume this is 1, then this is 2, and these should be 2 and 2. So, this is the relative sizing of these transistors for a CMOS gate. Now, let us see another important parameter, which is the fan in of a logic gate. So, what is fan in? Fan in says how many inputs can be connected to a logic gate. For example, here we see we have 4 variables A, B, C and D. It means there are 4 inputs which can be connected to this logic gate, that is called fan in. The same another thing is called fan out. Fan out is how many gates we can connect to a single logic gate. Let us say we consider this logic gate, how many similar kind of logic gates we can connect to the output of this CMOS. There is a limitation because each gate whatever we connect at the output, that is going to provide certain amount of capacitance at the load or the C out or the output node, and this capacitance is going to degrade our swings or degrade our timing information, or the delay is going to go higher and higher. So, there is an optimum number which we can put, which we can connect to the output, so that the delay is not very high, that is called the fan out. So, let us consider what is the fan in for a particular CMOS gate. So, for that let us say we have a 4 input NAND gate. So, earlier we considered only 2 input NAND gate, now we consider 4 input NAND gate. So, the symbol is, let us say this thing, this is NAND gate. So, instead of 2 we have now 4 inputs. Let us draw the circuit of this 4 input NAND gate, how it look like. So, we have in the pull up network we have 4 PMOS transistors connected in parallel. On the bottom we have 4 NMOSes connected in series. These are the pull down network. The 4 variables A, B, C and D. The same input goes to the pull down network A, B, C and D. This is the load capacitance CL. Now this is, we can see, if we can see this carefully, when this transistor, this A and B, where they are connected through a metal line, and that offers a local capacitance, a small value of capacitance, which we can call it internal parasitic capacitance. Let's call this capacitance is C3. Similarly, we have one capacitance here which is C2, and at this node also we have a capacitance which is C1. So along with the load capacitance CL, we have intermediate capacitances C1, C2 and C3 wherever we see the junction of two devices. So here these are the junction between, let's say, A and B, here B and C, here C and D. So we have three junction capacitances. This kind of model is distributed RC model, and sometime we use it for calculating the delay, that's called Elmore delay. In this particular case, we can write TP HL is nothing but 0.69 times R equivalent of N and C1 plus 2 times C2 plus 3 times C3 plus 4 times CL. So the delay of this network we can write through Elmore delay, which is 0.69 into R equivalent, the equivalent resistance of pull down network, multiply by the capacitance, the effective capacitance, because now we have three more capacitance along with the load capacitance CL, C1, C2 and C3. So we count from the ground. The first is the C1, so we write C1 plus the next capacitance is one level above, which is C2, so this is twice C2, so we write 2C2 plus the third capacitance, which is C3, which is 3 level above, so we write 3C3 plus the other capacitance CL, which is nothing but similar to C1, C2, C3, but now it is at the fourth level, so we write it 4CL. So this is the equation for the delay of this circuit, and this is called the Elmore delay of the circuit, and we can easily write C1 plus twice C2 plus 3C3 plus 4C4 or 4CL in this case. So we can see here very clearly the propagation delay, this TPHL, this degrades very rapidly if we have more number of stacking. So if we have more number of NMOS, or in other word we can say more number of inputs. So here we have 4 inputs A, B, C, D. So we have 4 transistors in series. So if we have more number of inputs, we have more stacking. So this term C1 plus 2C2 plus 3C3, this keep on increasing. And if it is increasing, then my delay is increasing, which is bad. So we can say that having large number of inputs to the gate is bad in terms of delays. So, the delay of this gate degrades very rapidly with the number of inputs we have. So, we can see that this delay degrades almost quadratically in the worst case. So, we can write it this point, this is very important point. The propagation delay degrades rapidly as a function of fan-in. And this can be quadratically in the worst case. So, now let us see how we can design these gates so that we have an improved or optimized delay from these gates. So, let us see some design techniques. So, the first technique is progressive sizing. In this type of sizing, if we have, let us say, NMOS ladder, let us say this is input 1, input 2, this is input 3, dot dot dot, we have, let us say, input N, and here we have this load capacitance CL. I am just showing here the pull down network only, which is the worst case analysis, and of course in between we have these intermediate capacitance. Let us say this is C1, this is C2, this is C3, and then CL. Then we can size them in such a way that this is, let us say, M1, M2, M3, and this is Mn. We can size them as a distributed RC line. where M1 is greater than M2, which is greater than M3 and greater than Mn. So in this, the MOSFET closest to the output is the smallest. This technique can reduce delay by more than 20-25%. So here we see that these pull up network and pull down network, they also have some intermediate capacitances in between, and by Elmore delay we saw that the worst case delay TPHL is nothing but 0.69 into resistance into the capacitance, which is the network of capacitance C1 plus 2C2 plus 3C3 plus 4C4. So to optimize the gate for having a optimum delay or the lowest delay, what we can do, we do the progressive sizing where M1 is the biggest transistor, then M2, then M3, then and Mn and so on. So M1 is kept the biggest one because all the current which is going to the top is flowing through M1. So M1 is the transistor which has to provide or discharge all the current coming from C1, C2, C3 and up to Cl. However, for a transistor Mn, if we look at the Mn transistor on this circuit, this Mn transistor only need to pull down the Cl only to the ground. The bottom transistor capacitor C1, C2, C3, Mn is not going to do anything for them. So this Mn transistor has responsibility only to pull down Cl. So this transistor Mn can be kept smaller. M1 is the biggest one because it has to sustain current from all C1, C2, C3. So this M1 is the biggest one. So we can do progressive scaling where M1 is kept the maximum, then M2, then M3 and so on up to Mn. So this transistor closest to the output is kept the smallest and the transistor closest to the ground is kept the highest in the width. So this technique can reduce delay by almost 20-25% in your logic circuits. So this is one of the technique we saw for optimizing logic gates for the delay, which is very important factor to achieve highest possible speed in electronic system. So this is all for today. Thank you.